the title's a bit cheeky. Obviously, I have not answered the question of what dark energy is, but I thought I would sort of have something a bit provocative because a lot of the theme of what I want to talk about today is really thinking ahead to when these models eventually will arrive, because I think it's only a matter of when, not if. And in particular, right, like this response seems a little cheeky, right? But we actually in lots of places in the news see things like this all the time in terms of calls to authority or calls to past experience. Oftentimes we see people who are experts who've gone through particular PhDs or from a particular institute give a statement, and as experts, who've gone through and understand what PhD programs are, what universities are like, we say like, oh, of course, we assign them some level of trust because of this. And the question is, what will it take if a model responds this way for you to say, that's good enough, right? This particular type of thing is enough for me to believe it. That's what I really want to focus on. Before I jump into things, I just want to highlight, so I'm partly here representing the art group, the Astrophysics research team. We have this super fun logo that one of our postdocs designed. So if someone is familiar with the original Hubble diagram, you might notice the positions of the stars actually mirror the original data as well, which was a fun touch. So we're an interdisciplinary group. It's co-led by Gwen Eady, who is 5149 Astro Stats, and me, who is 5149 Stats Astro. So together, we both combine to be 100%. So Gwen's amazing. She started the group and was my original mentor when I was a postdoc. We have 8 postdocs, 9 PhD students, and a lot of undergraduate students. You want to know more, please feel free to check out our website at astrostatut.com. It's fun. Also, it has a dark mode, very important. A very quick warning. So this is not a typical Astro talk. And what I mean by that is that there's a lot of astronomy work that I could talk about, and in fact, probably should talk about, but they will probably not be in this talk. This is all kind of half pedagogical, half rant, all unhinged. If you're interested in more, please check out either ADS, my website, our research page. I do a bunch of different stuff. Small shout out, for example, to like the new 3D dust map that we just released. Andrew Sagery is right here, who helped to lead that effort along with Catherine Zucker. We had, I'll present some new work that's been that just got accepted for publication, but there's a lot of other stuff we're working on. Most of it I'm not going to talk about. All of it's fun, but it's not relevant today. So what is relevant? Machine learning, or as we now as my students now kind of start to say, AI. And this is probably how a lot of us feel. I mean, I find that my usage of Claude when I'm coding has continued to increase monotonically day by day. And if we look, for example, at the literature in astronomy and other fields, we do see this huge rise in just this particular term. You can do a quick Google search, you can do lots of ADS searches and find that it really does look very exponential. So of course, the question is why, right? Why are people using this? It's just a vibe. The hype train is real, but I mean, there are real reasons why people are really focused on this, right? When I have lots of conversations with people, the number one reason people care is that it's just really fast, right? The thing is just whatever method exists is so slow. We have this increasing deluge of data. We need to process it quickly. People just want to go fast, right? I mean, we're in New York, but this is also true. The other thing that people really feel, and I get this a lot when I talk to people, is that it's accurate. People have this belief where they say, well, I could use this traditional method, but I want to do better, right? And they think ML is going to have them do better. And it consistently outperforms traditional approaches, asterisk here and quotes there, because this is, again, very overgeneralizing. The last thing is that it's flexible, right? How many times can you say, oh, I have this general method, and I can just drop it into any problem and it will do well? I've had many conversations with people who are oh, I just run XGBoost. I do it on this, I do it on this. How many times can you say that you take exactly the same 3-line block of code, give it a bunch of different data sets, and all of them it does very well? That speaks to something interesting that I hope to target today. So this type of ease of use, speed, and accuracy generally is why people like to use it. But it's obviously not so simple. If you look at the gap between number of papers that are posted on, say, the archive that use a particular ML method, and then you ask, why isn't, for example, DESI, in their recent press release, using the state-of-the-art deep learning, simulation-based inference, probabilistic machine learning framework to do their top-line cosmology results? Haven't we had tons of papers that could show that we could do this? The reason is because people don't trust these models, right? We just have this trend of publishing and publishing these things, showing that in theory they should work well. But when you have to get into it and use it on real data, people get scared. And the reason is because, not because this is wrong, but because understanding and trust for these models is really important. We have to really think hard about what we're trying to do when we apply machine learning to a problem. Are we just trying to predict a function? Do we really not care what the function is because it's some arbitrary thing that we're just going to marginalize over anyway? For example, fitting some random polynomial when doing spectral calibration. Are there particular astrophysical constraints that we care about? For example, redshift, rotation invariance. Do we need to understand how it works? Right? This is very important in many cases for scientific insight. What about error bars? Should it be aware of the fact that our data has measurement noise? Quality flags? Do we want visual inspection? How do we want to determine how things work? And ultimately, right, what happens if things go wrong? This is much more pressing in almost every other field besides astronomy, but it really does matter that in the real world, stuff will happen, and we need to know what's going to happen when a model is subjected under real pressure. So this is a very old meme, which is itself meta-referential, where back when Marvel clearly had a good model on training data, and then extrapolated that model to out-of-test data. And I think the performance of the MCU shows the results. This is why people are very skeptical, right? So ultimately, you could even ask, why do we even use AI in the first place, right? Given lots of these constraints, why do we keep doing it again and again and again? There's this really great essay. It's like 2 pages, recommend everyone reads it, by Rich Sutton, one of the founders of reinforcement learning, called The Bitter Lesson. And one of the top line takeaways that I want to just highlight for everyone here is the following, right? It's right here. The biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. The reason that he calls this essay the bitter lesson is because again and again, people say, if I can do handcrafted features, if I can use some particular bespoke method, I can do better. And they do for a few years. And then they lose. And then it happens again, and it happens again, and it happens again. And I see the same tendency. I have myself gone through the exact same train of thought. And I can see the writing on the wall that sooner or later, we are going to lose against scale. That's not a bad thing. And I want to argue exactly why this happens and how we can leverage this to our advantage. One thing that this does mean, though, is it's not surprising that a machine learning method does better than a traditional method. This is a given. We can look at like 1 million examples a day of machine learning is good. What really matters is not if it wins, but how it wins. That's where we learn something interesting from machine learning and from AI, right? That's where we do science. It's saying, what information is it leveraging that we were not able to take advantage of, or that if we took advantage of better, we could then improve our models? How can we use this to get feedback on what we're doing, the type of questions we're asking, and potentially what we can discover? That's what I want to focus on. And I think that foundation models are going to really open this up, but that's not what I'm working on. One is because I can't compete with Polymathic. I don't have hundreds of thousands of dollars. But 2, because I think this is ultimately a question that I'm really focused on is interesting. You can also see a good example of this, that there's this wonderful result or analysis I recommend people take a look, called Oil and Water Diffusion of AI Methods within and across scientific fields, that has shown that while these methods have become more popular, they have failed to diffuse broadly across many different domains of science. So you see essentially these new subfields open that use AI heavily, but they don't have large impacts that impact many areas of research within a broader field. And in particular, I want to go back to the opening question, where if you read in a press release that some collaboration used AI to discover the nature of dark energy, you immediately would be skeptical and to ask yourself why, right? If you went and read the paper, what are the things that you would need to have answered for you to say, actually, I believe this result, right? And how would those questions be different from a traditional method? If they're the same, that's great, but you might find that you probably would have more scrutiny to this than the previous one, and to think why that is. So the motivating question for this rant is not to ask what can machine learning methods teach us about data, because this is polymathic is going to win, and I don't have a million GPUs, I have one. It's how, right? I want to try and focus on how exactly we're going to use these things. So looking ahead to when these models are live, when they're here, what should we be focusing on? How should we be treating and approaching machine learning to derive real scientific insight and discovery? Yeah, you're welcome to ask me about it, but essentially I won't present any actual real foundation models here other than maybe a fun result at the end, but that's kind of it. So let's get started by saying, let's go back and say, why do we trust traditional models? What about them do we like? The first thing is, let's pick, I'm a stats person, which means that everything in this talk is going to come back to linear regression. The absolute best teaching tool ever invented, also just the best. So we have a linear model. It looks something like this. Why exactly do we trust this model, right? The one thing is that this model is easily interpretable. And what I mean by that is if you look at individual parameters in this model, it leads to specific impacts on an associated variable that directly impact in an easy to understand way the output. So you can look at this and you can say, okay, if I took the derivative, if I change my input by some small amount, it's going to have this effect on my output, right? It solves a lot of problems. The variables are interpretable because they correspond directly to a specific set of features that you're inputting. The impact on the response is very clear. You can pick and choose what specific variables you want to keep. So you can essentially build from the ground up all that intuition that you really want from a model. Of course, you can make this a little more complicated. You could say, well, maybe I don't use x, I use e to the x or cosine of x. Sure, those are all physical features that probably have real motivation, fitting a power law, fitting some phase function. Maybe the interpretation gets a little bit more tricky, depending on what framework you want to think of. Are you thinking of this as being the fundamental quantity of interest, that it's something about the phase? Or do you think that this is kind of a particular, shape, and you really care about, the particular impact at a particular position? Either way, still interpretable, right? And this also highlights one of the things about linear models that often is most misunderstood, which is that it's linear in the coefficients, right? You can change your input data whatever way you want. You can do all sorts of fancy feature engineering. As long as you have linear coefficients that multiply these things together, model still remains interpretable, still is great, still the best. That's one side. If you think about the data, there are other things about traditional models that are very appealing to us. One of the ways that we can think about this is looking at a curve like this. This plot sort of shows the risk. You can think of this as the loss or the error in the prediction, any version of this versus the capacity of the model. Now, capacity I'm going to use in a very flexible way to say how many parameters it has or how complicated the model can be. So think of like polynomials, for instance, as a good example. Now, the intuition is that based on just physical, things, most of the time when we look at data, we think that we should be able to compress that data down into a fundamental set of latent parameters, right? There's some noise that we observe in nature or some emergent phenomena, but it all comes back to being described by a few key numbers, a few key relationships, scaling laws. Meaningful explanations should simplify our data. That suggests that we want fewer parameters than data points. And the idea that as you make the model more and more complicated, it's not as effective, it's not as pretty, it's maybe not as physical. Naturally, this leads to the assumption that there should be some sweet spot where you kind of, minimize this risk of underfitting versus overfitting, and the model is maximally interpretable. You describe a lot of things about the data. You have essentially enough information to really figure out what's going on in that system. Here is sort of like this idea of overfitting. So what about that? Why exactly does this also appear by intuition? If you have more and more parameters, eventually you add as many parameters as data points, you essentially memorize them, right? So you fit a polynomial, you can go through every single data point perfectly. Sure, your prediction on data that you've seen already will be perfect, but your extrapolation to data you haven't seen will be way worse. So again, sort of as a conceptual example, think about fitting these real red points here. If you have a model that sort of is fit correctly, you might get something that looks like the black curve. And if you're overfitting, you might get something like the blue curve. Both of them might go through most of the data points, or in some way maybe not fit perfectly, but I would believe that the black curve is probably more accurate than the blue one. Both of these things match with our classical view. We fit a model, it should have fewer parameters than data points. It should not have too few because that's too simple. It shouldn't have too many because eventually it memorizes. So this sort of parabola of how well you expect it to do on the data you see, on the data you don't see, emerges very naturally. No math involved. This is all just intuition, vibes-based argument. So thinking about this, let's come up with a scorecard of how we can trust traditional models. And I want to answer these 4 questions, right? So on the left, I want to talk about linear regression. On the right, I want to talk about machine learning. So for traditional models like linear regression, are they interpretable? Yes, we build them that way. The parameters mean something, we construct them from the beginning. Do they have ways to accomplish measurement error and uncertainty? Yes, again, thinking of gradients and how they propagate through, very straightforward to think about how if you measure a certain thing, it affects the result, how the coefficients affect the result. Can you perform something like model selection? Yes, more complicated models are disfavored, too simplistic models are disfavored. There's one that should be just right. So there should be some way of finding out what that model is. Finally, is there scientific insight? Yes, right? This reduces the complexity of the data into an interpretable set of parameters. My claim is that for any machine learning model, we have to at least be able to answer yes, a clear yes to every single one of these questions. So we have to be able to say that we can come up with very concrete answers to these. I'm hoping I can at least prove that we have the tools, if not the exact results, to make real progress on those 4. So I will also say this is kind of work in progress over many conversations, iterations, particularly with Beeper Day, who's a Schmidt AI CETA Dunlap Fellow at the University of Toronto. If you have feedback on any of the stuff here, lots of questions, please feel free to just ask me or email us and we can try and incorporate it. Our hope eventually is that we'll write this up somewhere. Okay, so that's linear regression, my favorite part of the talk. Let's now talk about machine learning. So how do we trust modern models? To start with, if we look at this curve, one could ask the question that says, wait a second, at this point, I've like overfit my data, but like, what if I just added more parameters anyway, right? Like, you know, I have a 7-month-old son at home now, and if I just reach out and touch something maybe I'm not supposed to, what happens? And in fact, this happens, which is that somehow, as you add more parameters and data points, the model gets better. It gets way better. In fact, you can add more and more parameters, and the model gets so much better, it's even better than the original model. This is essentially known as double descent. It's the modern deep learning, machine learning kind of classic feature, right? And somehow, this asymptotes, so you can have an infinite number of parameters, and the model will still continue to improve. How is this possible? How can you fit more parameters and data points and have the model do better, right? How do we go from this, right, to this? You know, this is a real callback now too. That's, I think, the place I want to start with. Something is happening here. So the first thing is, let's go back to linear regression. Now, every time someone shows a neural network like this, it's a bunch of stuff, everyone goes through gradient descent. I don't care. Every time you see this, really what you should think of is that the neural network can be divided into 2 parts. One which just does a bunch of crazy stuff, and the last part is a linear layer, which means it just fits a linear set of coefficients to a final set of outputs that you care about. What does that look like? It means that fundamentally, neural networks have just 2 parts, a giant blob of things that learn features, and a final thing that just does linear regression. really what neural networks do, and what all these very fancy deep learning models do, is they learn how to linear regressionize the data so they can fit a model to the data that's just a line. That's all. Of course, the magic is in how exactly it does this, right? These are both happening at the same time, but for conceptual clarity, it's really good to think of it this way. So neural networks and deep learning fundamentally work because they are learning features. They are reducing the data into something that is easy to fit a line to. How does it do that? Why does that work? One of the key things about this is thinking about neural networks as fitting a curve, but also as thinking of any curve as really being a hyperplane in a higher dimensional space. And what I mean by this is if you think about, say, any input, this is say, x1, x2, and you transform it where you add, say, x1 squared, that actually lifts the data out of the plane. But if you do that the right way, you can actually draw a line through it, and everything now looks like it follows a linear relationship really well. In other words, if you think about fitting a polynomial, you have, say, a plus bx plus cx squared. One way to think of it is you're fitting an actual curve. The other way is you essentially add an extra axis to your data, that is x squared, and then you fit a plane in that higher dimensional space, not 1D, but 2D. As a direct example, here's what this looks like. So imagine you trying to classify these two types of things. Classification and regression are almost the same problem, just flipped in some ways. This is what you look at on the left. On the right, you can see that if you just add an x squared dimension, you naturally can draw a line between these two things. So you start with a smaller dimensional space, you add an extra feature, you augment your data, you learn something about it, and you do so in a way that you can split this in half. You can do this in fancier ways. Here's one where the correct version is mod 2. So if you do a simple operation, you can actually now cleanly separate this data as well. You can do this in more complicated ways. Here's a 2D one. If you lift it into a 3D plane, you can still draw a line that separates this data. This is what neural networks are doing. They're taking your input data, they're learning these transformations. Sometimes they're compressing, sometimes they're expanding it to be a higher dimensional space, just so they can essentially draw these hyperplanes through everything. That's ultimately what's happening at its core. So all this intuition about linear regression does in some way translate over to deep learning. Now, one of the key things in which we can draw intuition from this is to use what's called the kernel trick. So we've actually seen this idea before. So in my original example, I essentially said, well, let's change our features. Let's add like EX and do cosine and blah, 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 blah. This is just the disguise, right? I could have said this is now fitting some sequence of coefficients with some transformation, where this function essentially takes, x1 and x2 and broadcasts it to be e of x1 and cosine of x2. That's the same thing. And we just saw that this is what neural networks are doing. They're essentially learning this own function as well. So these are identical operations. Now, there's this amazing math result, and this actually proving this is so fast that it's actually kind of incredible. If you try and do linear regression where you say, okay, let me solve for what the best fit coefficient should be. I'm curious about solving for A. What is the answer? It turns out that the actual best fit solution, this is true in a Bayesian context and a frequentist maximum likelihood context. It turns out that the actual transformation itself never shows up by itself. The only thing that shows up in the equations is the inner product of the transform position of one point and the transform position of another point. They never appear isolated. What this means is that the actual transformation itself doesn't matter. What matters is how that changes the distances between 2 points. So if you have 2 points that start off at some spot, what actually matters is how your particular function, which is often called the kernel, changes the relative position of these at the end. And if you do all of the pairwise combinations of this, that really tells you what structure your model has learned. So there's direct equivalence between learning some features about ways to change your data and learning this kernel, which really tells you about the correlation between data points, how much point A and point B should relate to each other. And that can be extremely complicated. For linear regression, you can show this kernel is just essentially the dot product of the two. And you can rewrite every single classical result. So you can generalize linear regression to this nice form of kernel regression, where if you want to predict any particular point, y star, given some new observation x star, you can just do this, solve this equation, and you're good to go. So to summarize, right, why does this matter? This means, going back, that neural networks are learning some feature. But what really matters is how that's changing the relative distances between these points, which can be summarized by this kernel function. The kernel trick is amazing because it says that what matters is not the transformation, but the correlation structure that's induced by these transformations. The second is that because the transformation itself never is defined, you can actually do this even if the transformation is infinite dimensional. And there are easy examples. If people have done Gaussian processes, people talk about these radial basis functions, you can prove that actually that transformation takes one point and turns it into a function with infinite support everywhere. But because the dot product is well defined, the answer is actually totally cool. Now, why am I spending all this time talking about kernels? It's because if you think about what a neural network is doing, and you think about the fact that this feature representation and fitting this hyperplane is the same as a kernel, you might ask the question, does a neural network itself have a kernel that's associated with it? And the answer is yes. In other words, when you define a model, the architecture that you pick is you placing essentially constraints on the types of functions, on the ways that you think your data are correlated with each other. This is true both at initialization, so before you do anything with the model, when you specify the architecture, you've already essentially placed a bet on how you think the data will look like. It is also true after training. The first one is called the neural network Gaussian process. The second one is called the neural tangent kernel. You can definitely read about them more in some of the references there. There's also some great resources online. But this is real. So from one of the seminal papers on this, the top panel actually shows real function draws from a neural network at initialization. The bottom actually shows what this kernel looks like as you increase the number of layers in the model. The deeper the model goes, you essentially start with this very strong to much broader function prior. This is what deep learning is doing. When you initialize any model with any architecture, you are essentially saying how you think the data should be correlated. If you have chosen a good basis, right, you've chosen a good way that you think the data are correlated that represent the data very well, your model is going to fit it very quickly and very efficiently. If you don't do a good job, you're going to require a lot of data to sort of force and nudge everything to line up perfectly, and your model will perform very badly with the same amount of data. The other implication of this is that for neural networks, what really matters is not individual parameters, like in linear regression. You can think of them as groups of parameters that all move together, that all are correlated with each other. And it's the correlation structure among all of those parameters that actually are important. So for anyone who uses things like Gaussian processes or any of these other methods, neural networks are exactly the same. They fall in the same class of families. They make the same types of assumptions, even if those assumptions sometimes are implicit rather than explicit. But you can pull them out. Again, there are lots of caveats associated with this, but that's sort of the main takeaway. So, and just to show an example of this, here's like a problem where I love selection functions. You try and observe some data, there's some incompleteness, your survey is complicated, et cetera, et cetera. So this is something that comes up all the time. You have to correct for it. It's a huge pain. Looking at globular clusters, for example, this is really bad because they're often observed. This is a globular cluster on the top right when you can resolve it. But in practice, when you're out observing globular clusters in extragalactic context, they're just points. And those points are distributed around giant galaxies within galaxy clusters. So this was a fun project did with Bill Harris out of McMaster, where you can see just visually, probably will do a worse job of extracting globular clusters near the center of this, where it's outshone by the galaxy, versus at the edge. There are interesting chip effects that might affect things. There are other background galaxies here that could affect our completeness. So if we want to actually do this right, we need to understand the selection function for when we pick these things. Why would you use a neural network? Well, this is sort of doing these artificial star tests. This is a color magnitude diagram of inserting a bunch of globular clusters with different colors. The one on the right shows what you recover when you run it through essentially a full HST extraction algorithm. I think this is using Dolphode. Some of the features like these breaks are due to specific color cuts. You have to observe the thing in 2 bands in order to even detect it. If you then say, well, what is the completeness here? It's complicated. If you just marginalize over magnitude, so you just look at one of the directions, you'll see that there's more structure here and residuals relative to a simple fitting function, right? Which makes sense. This depends on, in some ways, the color distribution. I don't know if I think that this is necessarily an easy feature to capture. And if you then say, wait a second, let me go check how well I can model this. The actual observed data, now binned in number density, is up here on the left. So this is the artificial star tests. And if I fit a really simple linear regression model, in this case, logistic regression, I get this. Now, you might look at those two and say they're not the same. Right? Like in some ways, I'm like averaging across this sort of like behavior here, which makes sense. If I'm fitting a line and I don't have the capacity to really extend this or model this type of very sharp break, then you can get this type of behavior. But using a neural network, we can do a great job. So this is now showing the same sets of predictions for 2 of the clusters you're looking at, NGC 1275 and 3377. The top panel shows the actual number counts of the artificial star tests. The bottom shows the average predicted completeness in that. The thing you'll immediately see is that what these are doing is that they are really smoothing and averaging over a lot of these different features. And if you zoom in, you can see that really we're capturing lots of very complicated structure where you can see these 2 given banded regions that extend actually to quite high magnitude, which echoes the actual distribution we see in real data. And the key thing here is that this ability to capture this type of thing, that's the correlation structure that we assume for this architecture. And when I built this model, I specifically made it so that it was much sharper, using lots of these ReLU functions rather than much smoother using something like sigmoids. So this is again saying that when we are using machine learning, we can put in this knowledge, we can extract this knowledge, we can use this to our benefit. So going back to our trust scorecard, are they interpretable? Hopefully I've convinced you that fundamentally the answer is yes. The only difference is that rather than individual parameters being interpretable, we need to think of these giant models as having groups of parameters that all move together. And the thing that we interpret is the correlation structure that we have imposed on the data, and that the data has been learned from the data. That's what really matters in this case. So for the next part, I want to talk about errors, right? This is a big part of interpretability in astronomy. We always have noisy data. What can we do about it, right? What about uncertainties? There are tons of different ways to think about this problem. You have uncertainties on your data. You have uncertainties on the targets that you're trying to predict. If you have a supervised problem, your model itself potentially has uncertainties. How did you make the neural network? How did you train it? What parameters does it have? What about modeling uncertainties in the predictions itself? So if you think about a network like this can be quite hard to do. In theory, you could propagate errors through a model using like the chain rule, but this doesn't really answer your question, right? It doesn't really tell you exactly how to incorporate this into the full process of how these machine learning models work. It is very important, right? That's something that linear regression models can handle in an extremely straightforward fashion. Now, I'm not going to talk at all about this type of stuff. Although if you're curious about it, please let me know. I'm going to focus instead on the data. And I'm also going to skip all of the actual math here and just say that you can work through a lot of essentially integrals and marginalization to come to two main conclusions. The first is that when you start thinking of your data as being from some real distribution with some real measurement errors, some statistical framework, you automatically arrive at the fact that your loss function for your machine learning model is determined for you. There's a unique probability that's associated with your particular noise models. You are welcome to use other ones, but the main thing is that when people pick loss functions for various algorithms, if you know what the noise properties of your data are, if you know what your data look like, you actually have this already given to you, and you should use them, and you can do better when you do. So just for notation, by the way, whenever I use the tilde in these, that means noisy, and whenever I don't have it, that means that it's noiseless. If you want to know the exact solution that you need to solve this sort of tripartite integral, where you need to marginalize over the particular noisy observation given the noiseless, then the noiseless given the noiseless, and then the noiseless given the noisy. And this usually is inverted with Bayes' rule, and then you do some integral. It's a bit of a pain, but it's doable. I can give you code, and I can give you some advice for how to solve this. The key thing, though, is that I really want to emphasize, because I've made this mistake myself multiple times, is that if you just say, well, I'll Monte Carlo my way out of this problem by saying, oh, I'll just Monte Carlo the training data, I'll Monte Carlo when I predict, it actually is worse than doing nothing. You actually double count the uncertainties. There's some really nice toy examples I can give to prove this, but it's the worst. So when in doubt, just don't do anything. If you know what you're doing, though, this actually is the strategy to incorporate to solve this integral. It's just your loss function will look very different from what you think, naively anyway. And just to show this works, so we had a fun project with Zichang Sung, who's a student at Tsinghua, where we did this with photometric redshifts, but he had this toy example that I think is just so cool. So this is us trying to recover an underlying noiseless distribution from a very noisy population. So in this case, the gray are actually noisy samples. The blue is the intrinsic, and the red is the reconstructed. And you can see, if you look at the gray, and you actually look at the marginals, I was shocked that we actually can do this to some level of precision. You can see it's not perfect, right? Like in this case, we miss some of the structure underlying this example with two moons here. So the blue is sort of this 2-moon distribution that people use all the time, but it's totally doable. And this uses the exact strategy I just outlined. So it's not crazy, it does work. And you can also see this more general implementation in this SPI++ paper that was led by Bingzhe Wang. So just saying this, you can denoise data with ML. You can do probabilistic inference with ML. And in fact, I usually like to call, people use simulation-based inference all the time, but I really like to just call it probabilistic machine learning or likelihood-free inference because you don't have to use simulations. There are tons and tons of strategies to say, why are we predicting a number or a regression and not just predicting a probability distribution? And the proof that this probably is doable is essentially this very hand-wavy as follows. I've just ranted about how linear regression is great and all neural networks are kind of doing linear regression. And you could say, well, why only do one linear regression? Why don't we just do 3 of them? And we predict instead of the mean, we predict the median and then the 75th percentile and the 25th percentile. We could just do 3 regressions and learn 3 sets of coefficients. And if you just broaden that to say, well, what if we did 100 linear regressions and learned every quantile from 1 to 1 to 99, and then we turn that into a distribution and we use a neural network to model how all those coefficients change, you arrive at essentially a very hand-wavy proof that this should be doable. And in fact, it is. And there are multiple approaches to doing this. Diffusion models are very popular. They're super cool, but I won't talk about them very much. Normalizing flows are also awesome and super popular and ultra cool, and I will talk about them a little bit more. But that's what's shown here on the bottom, where you can see essentially that this distribution is being morphed from a Gaussian into something arbitrary by targeting essentially this density. Again, neural networks are solving all of these because this problem is fundamentally, in some ways, linear regression. Now, how do we combine these two things in practice? As a really simple example, I want to show this fun case with stellar ages and gyrochronology. This is work that was also done with Ruth Angus and Lucy Liu and Stephanie, who's here in the audience. So the main motivation for this, which starts all the way back when I was an undergrad and first was introduced to this, is that getting ages for stars is really, really hard. You look at the thing, it's a point, it doesn't tell you how old it is, you're like, ah. So one idea is that maybe you can use angular momentum evolution or stellar activity to do this, right? Stars sort of spin down as they age. You have magnetic fields drag particles out, stars should spin down, potentially their magnetic fields reconfigure. So in theory, this magnetic braking will cause the rotation rates to slow down over time. And it should be mass dependent. Different stars evolve at different rates. And so we should see different levels of magnetic braking and potentially different phase transitions between them. And despite dispersion in initial rotation periods, you can look at T-Tauri stars and other, protostellar populations, they should converge over time. So therefore, the idea is that we should be able to estimate the age of a star given its rotation period. Now, how does this look like in practice? Well, Phil Van Lane, who's a grad student at U of T, essentially went on this long process of assembling the largest catalog of rotation periods from open clusters to date. So we have over 7,000 stars and 30 clusters. And that's the data. This is log rotation period on the y-axis and EPRP d-red in color on the x-axis. And going from top left is the youngest and bottom right is the oldest. And by eye, you could say, oh yeah, I see these things look like they're moving. So sure, there's some relationship there. If you plot them on top of each other, you'd say, okay, I can still see a gradient, but that's a little messy. I don't know if I can fit a polynomial to that, but it's there, right? There is information there. So what Phil did was he built essentially a model to look at the conditional evolution of rotation periods given color and age, taking into account all these different observational effects, outliers, cluster contamination, all of the type of stuff that we've been talking about to really build a probabilistic model. And when he did this, here's the result. So this is what we get going from 10 million years to, in this case, 4 gig a year. But this is all done using a conditional normalizing flow trained on a discrete set of clusters. So every smooth evolution in age is interpolation between clusters where we have 0 stars that we've trained on. The smoothness and the sort of coalescence of probability at different places is a direct consequence of these different correlations that I just defined in the model before and that go into the thing here. So I remember looking at this and being like, this is so cool. The fact that we can even do this model at all, because I've been looking at this for years and feeling like I really would love to see something like this. So one of the things is that you can say, great, you can make a pretty plot, but can you actually use this to do inference to understand what is going on? The answer is yes. So if you go back to the clusters we trained on, you do cross-validation, you leave out clusters, you retrain the model. We find that we can predict on average cluster ages to within about 0.08 dex, 0.1 dex. That includes systematics. Again, doesn't include all systematics of exactly where the ages came from, but we've tried to benchmark those as best we can. If you go to individual stars, we find that the actual precision and accuracy of our model can vary wildly. In this case, here's a plot showing the actual residual in the age, as well as the precision of our posterior, in both in dex as a function of age and color. And this structure is all real and shows how different stars are really evolving as a function of time. But typically we find that we have a much larger per star uncertainty of about 0.7 dex. So again, this is just meant to be a preview of the fact that this does work. You can actually take uncertainties, you can use noisy data, you can build all of that into your model, you can deal with outliers, you can make them probabilistic. They all totally work. Now, you might ask, wait, but what do the error bars mean? Don't worry about it. We can talk about that later. But I thought about that problem a lot. Okay, so in sort of the last sort of bit of time, I'm gonna, in some ways, accelerate the progress of things, much like in ML, and hopefully people enjoy the really bad joke I thought of yesterday. Sorry, it's scaling the triangle. That's it. So if you look at this plot, you say, I'm missing something from this, right? This is a good picture, but don't I have other things that I care about? Of course. The first is that we talk about capacity of a model, but capacity is not the same as the number of parameters. It's the number of parameters given some architecture design. And if you pick a different architecture, again, like one with a different kernel structure, you could use a very simple model. You could use a more complicated one like transformer or convolutional or recurrent. In those cases, the same number of parameters will give you different correlation and potentially shift the location of this curve up or down. So the normalization might change. The second is that, of course, there's data, right? I haven't talked about how much data I'm fitting, but probably if I'm including more data, both this interpolation threshold will probably move a little bit, but maybe not exactly linear, but somewhat. But also probably the model will do better at the end. So the asymptote will also change. And finally, how about the compute? I've assumed that I can train these models for an infinite amount of time until they absolutely converge to the best fit. But maybe you don't have enough time to do that. Because I don't know, the models take like 10 or 100,000 like, H100s to run. And so in that case, you can imagine this whole curve really has an entire sort of waterfall like plot where as a function of how long you train the model, it will eventually descend to getting to sort of that best fit on the bottom. This is what's known as neural scaling laws. The fact that the performance of these models depends on the amount of compute that you have, the data set size that you're looking at, and the number of parameters that you use. And all of these are more or less like power laws, which is awesome because yay, power laws astronomy, right? But it also tells you something about we have a choice to make with these models. We can also use these to potentially investigate some more things. So for galaxy images, for example, Mike Walmsley is a Dunlap fellow currently in Europe for the Euclid meeting, generated a quick test of this, by looking at Galaxy Zoo. So he took a bunch of different images from all sorts of surveys. Here's an example here, and said, can I just throw a bunch of image models at this and see what happens? So here's the result. Each of these are split by different model architecture with different numbers of parameters. So from left to right is kind of like most complicated. The transformer hybrid model is here. This one is kind of like a transformer-like convolutional network, but they both are pretty similar. You can see just that the general scaling exists. All these things have kind of power law distributions as they move, but of course the normalization is very different. Models that are designed to fit these types of images better do way better with the same amount of data. So more trained data improves performance, and the trained data size has a greater effect than the model size of the architecture, but there are very, very strong differences depending on what you pick. If you fix the size of the trained data, though, and you make the models bigger, you find that indeed things also improve, but only up to a point. If you have only about 100,000 images, you really don't do a lot better as you make the model larger and larger and larger, more complicated. It's learned all it can from the data it has. But if you add a lot more images, not only does the sort of overall normalization change, but you can see that the models all still continue to improve, again, up to a point. So this is saying that at some point, you can't just make the model bigger if you don't have enough data to support it. That's not surprising. And I think that in astronomy, it's an open question as to where we're going to be in this regime as we start collecting more data. At what point do we need to switch strategies from one to the other? Putting this together, essentially, at least for Galaxy Zoo, the bottleneck for galaxy image and morphology classification is data. It's not parameters. We just don't have enough images to really crank at this problem. But again, if you have a better model, you can train much more effectively in the same amount of time. And that really does pay like in real energy dollars and not like burning up the planet to predict galaxy images slightly better. So in terms of this trust scorecard, I think on the model selection part, Machine learning is in a different regime, but the answer is still yes. We know the trade-offs between making a model bigger, adding more data, training it for longer, and how that affects how it's going to perform. That's a trade-off that we can decide ourselves, that we can understand these types of dynamics. And potentially, if you want to explore this further, I'm happy to talk about it more, about how we can use probabilistic predictions to go this forward. But I think that sort of makes the general point. Okay, the last part is ultimately the part that is the most hand-wavy, which is complexity. So at this point in the talk, this is how I feel. These models are very difficult. Even though I'm sitting here trying to reassure everyone that Skynet is not going to happen or something like this, at some point you have to say, like, well, what are we going to learn from these things? Where have I shown you that these models are going to teach us something or are recovering real astrophysical properties of interest that are cool? So again, going back to review, ultimately what matters is that these models are learning some intrinsic number of features. Those are not the same as the number of parameters in the model. That's like the first big thing to take away. There is some latent representation of your data, and that's not the same as how many parameters you've used to train your neural network. That sort of thing is in some ways kind of fixed. And really the model is about getting the correlation structure in place so you can learn those latent features. For traditional models, these two things are the same because you specify them yourself. But for AI and machine learning models, these big deep learning models, they're not. So again, if you're thinking about this, I find it really helpful to think about fitting this hyperplane and how many extra dimensions you can have to accommodate this sort of thing. In terms of learning, right, the real thing, what the bitter lesson tells us, and where I want to really focus this, is that we are telling the model how we want it to learn. We are leveraging all our expertise to say, here's what we think the data look like. Here's how we think that things are going to be correlated. Now take this and go do stuff with it. The better we can do that, the better these models are going to perform, and the more we can interpret the results because we know more about the ingredients we put in. Now, features in these models have two forms. Broadly speaking, we can divide them into dense or sparse. In language, which is where a lot of this is focused on, this is really sparse. You can think of dictionary learning, other stuff. In traditional physics, this is super dense. We like to think of, we have some complicated physics phenomenon, we can define it by some really simple equation, right? Newton's laws, these types of things. So generally, saturation occurs when the model has learned all the relevant features. So once it learns everything and we add on like more and more data, there's just nothing it can improve except maybe estimate the error bars a little better. Now, where are these features? Generally, people use autoencoders. So the idea is that you take your existing model and you say, hey, can I force you to like learn some subset of things that kind of can produce the thing again? So you kind of force the model to go through what's often called an information bottleneck or a dictionary to then reproduce the output. If the model can do that, then it means it learns enough information to be relevant here. Now, for large language models, I'll just quickly say, often people talk about sparse autoencoders. There's really, really great work by Anthropic. They're all online. Highly recommend you read them. This toy model superposition paper is like super cool. However, for astronomy, we often think of these as being dense. And so one example of this, of combining all these things together and trying to leverage them to learn something, was work led by Alex LaRoche, graduate student at UT, where we trained essentially this scatter VAE, so trying to infer essentially stellar spectra from Gaia XP, so shown here on the left, using 6 parameters plus 6 variances that we can predict to. We trained this model and we tried to reproduce the spectra. And when we do that, what we found was that even though it knows nothing about the stellar parameters and only looks at the data, has no ground truth, the only data it has is noisy Gaia XP coefficient measurements. It's able to learn real physics. We find natural divisions that seem to correspond really well to things like metallicity, to tracks in the Kiel space, which are shown here. These are 2D projections of various latent distributions, just showing that like we are really walking across these types of things. We've done the same where we can show, for example, here is actually crossing in metallicity on the giant branch or on the main sequence. You can see that actually we do see gradients in metallicity in these distributions too. We've done this also with alpha to prove that we have alpha sensitivity for this, so we can actually detect alpha elements with this model. But the main thing is that by forcing our model to learn dense features, we actually do a really good job of recovering some of these things. More recently, there's been this really fun project with an undergrad. This is Alejandro or Alex. So 2 Alexes, very confusing meetings, where we said, what if we actually added time series data onto this, where we took variable stars from ZTF with phase light curves from a paper last year, and said, what if we add this on and make our model multimodal? What do we get then? Here's an example of what we can show for the spectra. So I just want to zoom in essentially on one of these panels. The red show the actual real data. The blue show what our model recovers. And you can see immediately that our model is learning to denoise the data everywhere. So almost every spectra actually shows really nice denoising properties, especially on the blue end. So again, doesn't know anything about what spectra really look like. All it just sees is there are lots of spectra together with different noise properties. It learns to pool that information together, denoise them. The light curves are a bit simpler. So you can notice that in this case, most of the light curves, these are in the R band, kind of all look identical. They're pretty close. The model is able to reproduce them pretty well, which is really just the tee up to say, what happens when we look at the latent space? And in fact, when we put these things in, we get this. Now, I looked at that and I was like, oh my God, rings. But like, really, I said, okay, there has to be something going on with the fact that there are rings and the fact that the rings have some width. And Alex just yesterday, working really hard, showed, these are, I think, like the coolest GIFs ever. If you go around here, this is phase. This is phase in the light curve. And it actually maps in this sort of latent dimension perfectly as you move around. So the model naturally recovers, knowing nothing about phase, ideas about phase, and learns to encode that symmetry in the data. Again, not like, revolutionary, but I think it's so cool. And if you do the opposite way, and you instead say, well, what if I go from the inside out? The model learns temperature. This is the type of thing that multimodal models can potentially unlock for us. The fact that for this particular series of eclipsing systems, which are eclipsing WMOS systems, there is a correlation between the temperature of the star and the particular shape of the light curve, and that gets encoded in this particular structure. That's stuff that, for example, I didn't know because I don't do variable stars, but as soon as I showed it to Maria Drought, it was one of the things she's like, oh yeah, that makes perfect sense. So to conclude, because I know I'm very close to the end, I hope the answer is that you can see here is that I really believe the answer is yes. We're building up the tool set, the language we need to extract real interpretable scientific insights, not just in this fun like toy way, but in real actual live data sets. And I do believe that the type of models that are being built by Polymathic, by other groups, are going to unlock this type of stuff if we can apply these things to them. So I just want to close by essentially saying, I hope that I've answered this general question, not about what necessarily can teach, but how exactly these models can teach us about stuff. And hopefully I've helped all of you feel like you can be a little bit more both skeptical and sort of informed and I'd say deliberate about how you want to use these models to accelerate your own research and your own discovery. So to summarize very quickly, I talked about sort of these different ways of thinking about training and test risk, how we can think about feature learning as both curve fitting and high dimensional projection and fitting of planes, how that turns into a particular kernel structure that we can then apply to data, for example, with trying to estimate selection functions, how we can then use, for example, probabilistic modeling to extend this to answer questions about, for example, stellar activity evolution and rotation evolution, how we can use scaling laws to investigate similar questions in astrophysical data sets about how much more data we need, what type of models we're looking at, how we expect to perform in future work. And of course, using these types of encoders to extract what I think are like fun examples of learning real structure from Gaia XP spectra without knowing anything about stellar evolution. Again, ultimately, we'd like to encode this type of knowledge into the model directly, but just showing that this is possible and that we have tools necessary to extract this, I think is very powerful. So with that, I would like to close, and hopefully my rant was not too bad. So thanks, everyone.
Thanks, Josh, for that exciting and stimulating talk. Let's open it up to questions. In the back, let's start with Julianne.
That was a fantastic talk. Thank you very much. I'm going to be like a little provocative here, but I'm actually like interested in your opinion about about next steps, right? I mean, a lot of this, for me, a lot of the biggest successes in applications of machine learning to astrophysics have been a little bit more on the engineering side, like, can we denoise things? Can we separate populations? Can we map out feature spaces? But, if you didn't know something about metallicity or stellar evolution, so like, it's cool as all get out that like these things are mapping into interesting spaces that are separating stuff out, but the ability to do anything with that is so when I think about like when you're saying about like, oh, it's interpretable, I don't think it is interpretable given knowledge we already have.
Yes.
I'm not seeing lots of examples where it's pushing into like I am generating new knowledge about the physical world as opposed to I'm taking my knowledge of the physical world and what's interpretable is my space of what my model learns. And I'm kind of curious how, like, I mean, these things are incredible accelerants to all kinds of things. I'm curious about where you see that next phase going. Because I kind of think it's a little, those two columns in your thing are talking about somewhat different things. So I'm just kind of curious where you think the next steps are, how far you think this goes, et cetera.
That's actually a wonderful question. I agree with you fully on the, a lot of these are sort of like, well, we see this is true because we know sort of kind of what the answer looks like. And so we're using that to interpret the results. So my feeling is that we still need to do more work to really, I'd say, turn these particular late representations into more interpretable versions. A lot of the stuff for large language models is still actively being developed. I think some of the work on dense autoencoders is, has a lot of room to grow, and potentially thinking about ways that we can transform the space or linearize the space to give us things that are somewhat aligned with things that we know, but that leave space for things that we don't know to behave in similar ways is probably going to be one of the best paths forward. So, I suspect that some elements of like geometric learning or thinking about volume elements or particular ways in which you want to establish a privileged basis in your latent representations or conditional bases in the latent representations will be a big factor going forward. So that's not a direct answer because I actually don't think that at the moment we have a full suite of tools to answer exactly those questions where we'd say, I want to infer or discover something new about how all these abundances change together without knowing already what those abundances are. But I think we're moving in the right direction for that. On the second point, in terms of what we could do, I think the potential of lots of these things, especially for multimodal models, is finding patterns or particular associations in the data that we weren't necessarily aware of that were there, or if we knew they were there, we just didn't have any constraints on essentially the functional form they could take. In that case, the interpretability is less relevant than just getting sort of those correlations out and being able to study those and just having that tool available so we can say, great, now we have a concrete way of simulating in a very statistically rigorous sense. For example, how the infrared emission from a galaxy corresponds to the UV emission of a galaxy, or how exactly we expect a star's rotation rate to evolve over time, or how stellar activity might correlate with magnetic activity or chronospheric activity of a star. All these data sets exist and the correlations are known, but sort of the exact structure is not. And that might be enough for us to then go back to models and say, great, how do we reproduce things that have this exact Fourier spectrum, that have this sort of wavelet decomposition that these models are able to learn? So again, I think that your question is spot on in terms of right now, I think we are still trying to figure out how to move from using our own basis of labels that we know to interpret the space to then flipping that around and saying, can we derive sort of a new set of bases that are in some ways informed by the ones that we have, but that have potential for new discovery? Yeah, hopefully that's a long answer, but I hope it's okay.
Okay, we have time for one more question. I think it's on Amy or no. Do you have a question?
So yeah, speaking of interpretability, in the rotation age normalizing flow video you have there's a very interesting structure kind of at the bottom where there's a sharp edge that I don't really know what to make of.
Yes, so that one actually, Stephanie, you were just talking about this. This is like the craft break that comes in. So.
Oh, yeah, on the left side.
Yes.
The high mass stars, yeah.
Right over here.
The things on the left, which we did end up clipping out.
We clip out of most of the predictions.
Before we tested it, yeah.
Yes.
Yeah, things with radiative outer layers don't break.
Yes.
Okay, but what I mean is like the bottom line there, is that the thing?
You're talking about the movie that's in the upper right.
Yeah,
right?
movie in the upper right.
Yeah.
Just like there's kind of a limit like in the bottom where like there seems to be kind of a little bit of a sharp transition there.
So some of those are artifacts of the data. Yeah. So that one is in particular a data artifact where if you actually try and sample from it, it's essentially not there because it's so thin.
Sure.
But it just shows up because the cutoff is sharper in other areas.
Sure.
So that's our artifact. Yeah.